Okay, I am reporting on joint work with Tony Hill and Jerry Hopkins, both of whom you probably know as Mike. But as a co-author, I needed to have distinct names for them, and these are based on their middle names. Their full names are Michael Anthony Hill and Michael Jerome Hopkins. So I address them as Tony and Jerry. Okay, so so the HHR theorem is about the following. Okay, there are hypothetical elements known as theta j that live in this dimension in the sphere spectrum, and they are detected in the mod 2 atom spectral sequence by the element Hj squared. So that lives in this X group. Now, emphasis is on the word hypothetical. They were thought to exist. In the 70s, now that this relation, these elements came up in the work of Kervaire and Milner. In their classification of exotic spheres. Now, I don't want to go into that in this lecture. That would take me too far afield. What that connection is. Browder showed that if these elements exist, they're detected by this element, and that made them real. That sort of raised the stake for stable homotopy theory, because they're hypothetical elements that are related both to the classification of differentiable structures on spheres, and they're important elements in the atom spectral sequence. And so this was known, this connection was, this is Browder in 1969. And the Kervaire-Milner paper, I think, appeared in 1963, I'm not sure. Now, once Browder's theorem was proved, everybody wanted to find a way to construct these elements, and many people tried in the 70s to produce these things, and they all failed. Now, what we know about it is we know that theta j exists for j equals 1 through 5, and I can even tell you what the first couple of them are. Theta 1 is the same as eta squared in pi 2, where eta is the Hopf map. Originally constructed as a map from S3 to S2. Theta 2 is nu squared in pi 6, where nu is another Hopf map, one map constructed by Hopf from S7 to S4, and Hopf constructed a third map known as sigma from S15 to S8, and theta 3 is the square of that guy. Then there's theta 4 and theta 5, which don't have such simple descriptions. Their construction is more complicated. Now, the theorem we proved is that theta j does not exist for j greater than or equal to 7. We don't know about the status of theta 6. Theta 6 may, as far as we know, theta 6 may or may not exist. And if it does exist, it's in the 126th step. Now, so I'm going to give you the barest outline of the proof. And then gradually fill in more and more details as time goes on. So the main idea is we construct a certain spectrum that I'll call omega. That has three interesting properties. And each of them is a theorem. So the first one is the detection theorem, which says the following: if theta j exists, its image in the appropriate homotopy group of this spectrum is non-trivial. So this spectrum will see any thetas that exist. Secondly, periodicity theorem. This spectrum is not connected. It's a periodic spectrum, and the period is 256. In fact, it's pi. I wanted to write that it's equal to its 256th loop space, but then I'd get into trouble with the symbol omega, so and then the third is known as the gap theorem, which is a statement about certain homotopy groups of omega, named in small negative dimensions, namely pi I of omega is 0 for 3 values of I. In particular, -2. -2 is the interesting one. Okay, so Okay, so then if you know these three things, then you can say 2 and 3 imply that pi 254 of omega is 0, and 254 is the dimension of theta 7. So, and remember, the detection theorem says if theta 7 exists, we will see it in this homotopy group. But this homotopy group is 0. So that means theta 7 cannot exist. And similarly, any higher theta j, the dimension of any theta j j is any integer, at least 7, its dimension is congruent to -2 mod 256. So we're out of luck. So none of these higher thetas can exist. So this depends. So the theorem rests on this spectrum omega with these wonderful properties. Now, how do we get this omega? Well, this is where equivariant homotopy theory comes in. We need equivariant homotopy theory to construct omega. So, last month I gave 3 lectures about orthogonal G spectra and how to put a model structure on the category of such. So, I'm going to need some of that now. So the first thing I'm going to say about this spectrum omega, now this is an ordinary spectrum. This omega is an ordinary spectrum. It's not a G spectrum. It's an ordinary spectrum, like you learn about in school. However, it's constructed by equivariant methods. In particular, there is a C8 spectrum that I'll call omega tilde, and then omega itself is the C8 fixed point set of omega tilde. Now, I want to remind you what that means. So, recall an orthogonal G spectrum X. So G here is any finite group. Okay, an orthogonal G spectrum is a functor from a certain category called JG into the category of called TG. This is the category of pointed G spaces. And this category, this is the Mandel-May category. And in this category, the objects are orthogonal representations V of G. So that means there's a collection, so you have a collection of, okay, so X is this functor, so, so the value of X on V is denoted by X sub V, and then there are certain structure maps. We've got two representations, V and W. Then there are structure maps that look like this. And this space JGVW is a certain finite dimensional GCW complex, which can be explicitly described. I won't go, I did that last month. The details of this are not important. But anyway, this guy is a certain finite GCW complex. Now I can tell you how to define the fixed point spectrum of such a thing. So, so X upper G is an ordinary orthogonal spectrum. Which means this is also a certain functor. So it's a functor from a category that I'll call J without the subscript, and it takes values in T, which is the category of pointed spaces. And this is a category whose objects are just finite dimensional vector spaces. So this is also known as the Mandel-May category. And in this case, the objects are just finite dimensional vector spaces. There's no G action. So, so xg is a functor from this category to this category, so I have to tell you what its nth component is for in each case. So the nth component of xg is the following. Now, I have my functor x from the Mandel-May category to pointed G spaces. So the objects in this category are finite dimensional orthogonal G representations. In particular, I can consider one object in this category is Rn with trivial G action. No G action at all, trivial G action. So that's, okay, so x sub n, by definition, is a certain pointed G space that's given by this functor. This functor assigns to every representation of G a pointed G space. In particular, it's assigned such to representations with trivial action, and that's what that's the one I want to take. So this guy is a pointed G space, And I can take its fixed point set. This thing in parentheses here, Xn is a pointed G space, so it has a fixed point set. And that is the nth space in my fixed point spectrum. So the reason I made this definition is that I told you before that omega, the spectrum with these wonderful properties, is the fixed point spectrum of another spectrum that I'm calling omega tilde, which is a C8 orthogonal, an orthogonal C8 spectrum. So I now have to tell you what this omega tilde is. What is the orthogonal C8 spectrum omega tilde? So I'm going to start with a C2 spectrum, which I hope is somewhat familiar. Then I'm going to describe a construction for that enables you to take a C2 spectrum and do something to it and get a C8 spectrum. And then I'm going to take the C8 spectrum that I get and I'm going to do something else to it in order to get omega tilde. So, there is a C2 spectrum known as MUR, sometimes referred to as real cobordism. And it was described a few weeks ago in this room in a talk by Leonard Meyer mentioned this in a talk that he gave a few weeks ago. I'm sure you all remember everything that he said. I will tell you part of the story. So it's a C2 spectrum. That means, so in terms of this definition, it's a spectrum, it's a collection of C2 spaces, one for every representation, orthogonal representation of C2. Now, I'm not going to tell you what all of those spaces are, but I am going to tell you what some of those spaces are. You can there's internal structure in the category of such spectra that means you can uniquely identify a spectrum by just saying what values it has on some representations. You don't have to do it for every representation. And in this case, to define a C2 spectrum, X, it suffices to define these guys in rho, where rho is the regular representation of C2. In fact, you can make a similar statement for any finite group. If you want to define a G spectrum, you just need to know what it does on multiples of the regular representation, and everything else will that'll determine its homotopy type. So Now, the regular representation of a group is, by definition, you consider consider a vector space whose dimension is the order of the group, and you think of a basis of this vector space as being elements of the group, and the group permutes the basis elements, and that gives you a representation, and that's the regular representation. Another way to think of, so that means in this case we got a two-dimensional vector space, and C2 acts by permuting two basis elements. Another way to think of it is this is isomorphic. This two-dimensional real vector space with the C2 action is isomorphic to the complex numbers with the action by conjugation. And if you want, you can think of, if you want a real basis for the complex numbers that gets permuted by the action of C2, let's say 1 plus or minus I. Those are two complex numbers. They form a real basis of this two-dimensional real vector space, and they get permuted by the conjugation action. So rho is isomorphic to complex numbers under conjugation. And so I'm going to tell you what the nth row space of this thing is. So I'm going to take MUN, that is the Thom space for the universal complex n-plane bundle. And this can be constructed out of Grassmannians and blah, blah, blah. And there's complex conjugation acting on everything in sight. If you're talking about the Grassmannian of complex n-planes in some bigger complex vector space, you have conjugation acting on everything in sight. So this space comes equipped with a C2 action. And that gives you a spectrum. Now, in practice, you may want to take its fiber replacement or blah, 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 but we don't need to worry about that right now. Anyway, you get a spectrum, and this spectrum is denoted like this. So that's a C2 spectrum. Now, remember, what I'm looking for is a C8 spectrum. So I'm going to tell you how to get from a C2 spectrum to a C8 spectrum, or more generally, how to get from how to get a G spectrum out of an H spectrum where H is a subgroup of G. So let H be a subgroup of G, finite groups. And then here's some categories that I want. So top H is the category of H spaces and equivariant maps, H maps. G is the same thing for G, and there's also pointed analogs. T upper H stands for the category of pointed H spaces and pointed H maps, and TG is the same thing for pointed G spaces. spaces. Now, if you have a G space, pointed or not, it's automatically an H space because H is a subgroup of G. So if G is acting and subgroup is acting. So there are forgetful functors. I'm going to denote like this, I upper G, lower H. And I'm going to use the same notation in the pointed case. Okay, you have forgetful functors. And it turns out that they have both left adjoints and right adjoints going the other way, and I'm going to tell you what they are. So it has a left adjoint. So the left adjoint is going the other way. So I start with an H space X, and I want to build a G space out of it. So the way I do it is that I take the Cartesian product of G and X and mod out by the action of H, and that's so I'm thinking of H as acting on this G by right multiplication, and then G is acting on this by left multiplication, and then so you get a G space this way. Now, it's easy enough to check that this is a left adjoint to the forgetful functor. Now, the forgetful functor also has a right adjoint. Oh, now, let me see. Let me make some remark about this. The underlying space here, the underlying space is the underlying space is the Cartesian product of the set G mod H with X, and then G. So this is a discrete. This is a finite set of an appropriate order, and so now we're looking at a finite number of disjoint copies of X, and the group G acts by permuting these summands, and in such a way that H leaves each summand in each piece invariant, and H acts on X in the prescribed way. Now, there's also a right adjoint that I'm going to describe. And the right adjoint is this. Right adjoint sends X to the space of H equivariant maps from G into X. So X is an H space by definition. G is also an H space. So we're looking for H equivariant maps from G to X. And this space is underlain by the following. It's a Cartesian power of X, where the number of factors is the index of the subgroup. And here, the group G is permuting the Cartesian factors, and it's doing it in such a way that the subgroup H leaves each factor invariant and acts on it accordingly, acts on it as prescribed. So all of this is in the unpointed category. This is, remember, top G is the category of G spaces without base points. Top H is the category of H spaces without base points. Now there are pointed analogs of these constructions. Okay, so in the pointed analog of this, instead of a disjoint union of this many copies of X, you have a wedge of this many copies of X. And for the right adjoint, instead of a Cartesian product, you have a smash product. So you have a G mod H fold smash product of X with itself, and the group is still permuting the smash factors and so on. And this guy has another name. I'm going to call this the norm of X. Okay, so the norm is a way to get from a point. The norm is something you can do to a pointed H space and get a pointed G space, where G is a supergroup of H. Now, I'm going to wave my hands a little bit and say that there's an analogous construction to this on spectra. There's an analogous construction on spectra. So there's a way to take an H spectrum. There's a functor from H spectrum to G spectrum. I'll denote the same way. Now, remember, we have a C2 spectrum of interest, namely this. This is a C2 spectrum of interest. So I can do this construction to it and get a bigger spectrum that is for any group containing C2. I can make if G is any group containing C2, I can get a G spectrum by doing this thing to MUR. So. Okay, so I have this functor for any groups G and H. H is a subgroup of G. So in particular, I have this if H and G are C2 and C8, and I'm going to so I have this functor, n lower C2, upper C8, and I'm going to write it like this. I'm going to be lazy and write it like this, N28 or N82. So then, so I can take this functor and apply it to MUR. That's the spectrum over here. So I get a spectrum with a C8 action, and it is underlain by the fourfold smash product of mu. That's the underlying spectrum. It's the fourfold smash product of mu. C8 is acting on that by permuting the four factors, and each factor is invariant under the subgroup C2, which acts on it in the manner that's prescribed by this description here. Maybe put an R here. So I take the fourfold smash product of MUR and have C8 act on it in a particular way. Now, you may wonder why C8? That's a fair question. Why C8? Why not C4 or why not C4 or C16 or whatever? And the answer to that question is if we did this with C4, or if we didn't do it at all, we just start with MUR itself. MUR doesn't detect the Kervaire invariant elements. Doesn't detect them. Nor does the, and if you norm it up to C4, it still doesn't detect them. If you norm it up to C8, it turns out that it does. It also detects it if you norm up to a bigger group, say C64, whatever you like. Now, the problem with norming up to a bigger group, say you wanted to norm up to C16 instead of C8, then you would you'd still get detection, and you'd still have the gap theorem, but the periodicity would be weaker. The periodicity would be you'd have a larger periodicity. I forget what it is. It might be, let's say it's 2 to the 11th. I'm not sure, or 2 to the 13th. Let's say it's 2 to the 13th. I don't remember exactly. But what would that buy you? That would tell you that theta j doesn't exist for j greater than or equal to 12 instead of j greater than or equal to 7. So you'd still get a theorem, but it would be a weaker theorem. You'd have you'd have to start at a higher, you'd have to start above theta 7. You'd have to go up to theta 12. So
the periodicity is bigger than 2 to the 8, and it's not 2 to the 9th.
No, it's a lot bigger. I think it's 2 to the 13th. There's a formula for it in the paper. I don't remember. Yeah, it is. It's definitely not 2 to the 9th. It goes up faster than that. Anyway, that's why we pick C8. That's what's, anything smaller. If you use a smaller group, you won't get the detection theorem. If you use a bigger group, you'll get the detection theorem, but the periodicity will be much greater. So the conclusion will be a weaker theorem than what we have. So that's why C8 is the optimal group for this purpose. It's the smallest group that'll give you a detection theorem.
And what about the gap theorem?
The gap theorem works for any group, as will be explained. The gap theorem is cool for anything.
Does it get bigger?
No. No, you always have a gap theorem. That's a good thing. Okay, now, so this is a C8 spectrum. It is not the spectrum. We're not here yet. It's not omega tilde. Remember that one of the theorems I wrote down to begin with was the periodicity theorem, which says that the homotopy groups repeat every 256 dimensions, which means that the thing certainly isn't connected. It's a periodic spectrum. And when you do this norm construction, you're not altering the connectivity. You're not going to, this norm construction isn't suddenly going to give you cells in negative dimensions or homotopy groups in negative dimensions. So this is not going to, this spectrum is not going to do it for us. We could look at the C8 fixed points of that spectrum, and who knows what it is, but it won't have a periodicity theorem, so it's going to be a lot harder to deal with. So I'm still one step away from omega tilde. So, so what do I have to do? Now, I have to explain something. Equivariant spectra, G spectra, have homotopy groups that are graded over ROG. That's part of one of the features of it. They have homotopy, not just homotopy groups graded by the integers, but homotopy groups graded by the representation ring of G. And in particular, now, this is going to seem like a rabbit out of a hat. There's a certain map of interest that goes from S19, row 8, into this thing. Y19, that's an elaborate calculation that I don't have time to do right now. I may do it in some future lecture, but right now, just take my word for it. There is an interesting, I'll call this map delta. There's a certain map that is of interest for this purpose. Now, this thing is, MUR is a E infinity ring spectrum. It's actually, in the orthogonal world, it's actually a strictly commutative ring spectrum. You can have such things in the orthogonal world. And when you norm it, when you take the norm, that preserves that property. So this thing is, this is a ring spectrum with all the nice properties you could hope for in a ring spectrum. In particular, I could smash both sides of this equation with this spectrum. I'm going to abbreviate this spectrum by X. So, so I have a map like this. So I'm smashing both sides of this with X, and so I get a map like this. And then and then X is a ring. So I get a map like that. So I have a map from this suspension of X to X. And I want to iterate that map and take the homotopy colimit. So, okay. So using this composite map here, I can do this. I can iterate it like so, and I can take the homotopy colimit, also known as the telescope. And that's what omega tilde is. Okay, that is omega tilde, and it is a C8 spectrum, so it has a fixed point spectrum. Now, we know hardly anything at all about this C8, the C8 fixed point spectrum, C8 fixed points of this telescope. All we know is the three theorems that I mentioned at the beginning of the lecture. It's a bitch to get a hold of this thing. It's really a big monster. You know, it's very hard to calculate with, and all we actually know is what I said at the beginning. I can't tell you what pi 57 of this thing is. I have no idea. I just know what I said at the beginning.
Is this Bowsford localization in some?
What?
Is this a Bowsford localization?
Well, maybe, but it's, you don't need to use those words. It's the homotopy colimit. I mean, there's an explicit map here. There's an explicit element that I didn't say what it was, but this thing has an explicit description. It's a certain element in the homotopy of this C8 norm of MUR, and so you can use it to construct these maps, and you can take the homotopy colimit. You don't need to say Gauss-field localization. It may be in some suitable sense, but it might be if it's any Gauss-field localization, it's probably the fourth chromatic localization. But you don't need to say that. You don't need to know that. You don't need to say that. You just need to know that. You just need this. You just take the telescope of this construction. Okay, so so now the question is, how do you deal with something like this? And I've only got 5 minutes, so I'm not going to start a new topic. I'll continue this next week, and I'll just say. So all I'm going to say now is that there is. The homotopy of this okay, and star here, 5-pointed star means ROG graded homotopy. The homotopy of this gadget can be studied using the slice spectral sequence. Now, I'm not expecting you to know what that word means. Anyway, I will construct the slice spectral sequence next time. There's a new computational tool that we invented that works very well for this gadget and enables us to prove the detection, not the detection, but the gap and periodicity theorems. The slice spectral sequence enables us to prove the gap and periodicity theorems. The detection theorem can be proved with what I call 20th century technology. That is, you can do various calculations using chromatic techniques that were available 20 years ago to prove the detection theorem. But the periodicity and gap theorems require equivariant techniques, and as far as I know, can't be done any other way. So I will talk about this slice spectral sequence next time. So that's all for today. Yes.
Is there any chance if you norm MU up to, like, norming it up to a big cyclic group is probably terrible, but if you norm it all the way up to S1, possibility that there's any clear out in the homotopy groups?
I have no idea. I don't know. I've never thought about norming up to S1. I know there are people that like to do that, but I get squeamish. I mean, even norming it up to the 2 torsion in S1 would be bad. I mean, it would be a mess. It could be done. I mean, there's this norm construction you don't have to have you don't have to have finite index in order to do that. So yes, you could. There is a norm. It is possible to norm up to S1, but I have no idea what you get. And as I said, the bigger the group that you norm up to, the longer the periodicity. So you might get something very beautiful if you norm up to S1, but periodicity probably wouldn't have any periodicity at all, so you wouldn't have any way of. So and even if the gap theorem holds, it wouldn't buy you anything because you wouldn't have any periodicity. So it's an interesting question, but I don't think it's going to lead to an easier proof of this theorem.
And you said that omega is the actual fixed point of omega Torah. Can I also think about this if I forget from a covariant spectra to naive spectra and take the homotopy fixed points, will this give the same?
It turns out that the homotopy fixed points and the actual fixed points are the same in this case, but that's a theorem. That's not obvious.
Is this a Galois extension?
I don't know.
So Doug,
Yeah.
will there be like, say, if you're doing only for finite group, will there be any subtlety about, like, say, if you norm into a billion group or you norm into like a non-billion stuff, or there's a kind of central condition going around when you do conversion?
Well, it depends on how the constructions don't depend on groups being abelian. There's no abelian hypothesis in any of these constructions. How it would be to actually calculate, I don't know. I don't know what kind. When you get down to nitty-gritty calculations, I don't know what you're going to. Are you thinking of norming? You're thinking of norming up to the quaternion group, aren't you?
Right. There's a certain construction in the HHH paper can only be done if every element is central, meaning it's a billion.
Okay, so yeah, you've mentioned this before, and I haven't gotten to those constructions in this lecture yet. Right. There's some more delicate calculations that go into this that I haven't gotten to yet, and yes, they may break down if the group isn't abelian. That's for the future. Woohoo.
So I have a naive question. So how did you come up with that?
How did we come up with it? We had been. So I have a metaphor for this. We were hiking in the Alps and we found a shortcut up Mount Everest. If you go hiking in the Alps, you're not expecting to find your way to Mount Everest. And we weren't expecting to find a proof of the Kervaire Invariant Theorem. We didn't sit down one day and say, well, let's see if we can prove the Kervaire Invariant Theorem. We were starting in, when was it? 2007 or 2005. We were thinking about trying to find the homotopy groups of, you've got this theorem that says that the Morava stabilizer group acts on the Lubin-Tate spectrum in an interesting way. And the homotopy fixed point set of that action is the Kn local sphere. And that's very difficult to calculate, but you could take your favorite subgroup of the Morava stabilizer group, and it also acts. So we were looking at finite subgroups of the Morava stabilizer group, and it so happens that let me see, how does this go? The fourth Morava stabilizer group at the prime 2 has an element of order 8 in it. You can check that. It has The fourth Morava stabilizer group has an element of order 8. The 2 to the nth Morava stabilizer group has an element of order 2 to the n plus 2 in general. Anyway, I think I was out of the room when the real big breakthrough happened. I'm not sure exactly how it happened. You know, these guys were at Harvard and I was in Rochester, so I didn't get all of the. I wasn't there for all of the conversations. So I can't really. You get a better answer from Tony or Jerry. You get a better answer from one of them. But we had been studying the homotopy groups of homotopy fixed point sets of finite subgroups of the Morava stabilizer group acting on the Lubin-Tate spectrum. We've been looking at that, and so we were sort of tooled up for this sort of thing. And then either Hill or Hopkins or both of them came up with this idea of using the norm of MUR instead of the Lubin-Tate spectrum. You'll notice I have not mentioned the Lubin-Tate spectrum in these talks. And the nice thing about these norms is the group actions on these norms are really transparent. It's very explicitly geometrically described. The group action on the Lubin-Tate spectrum is somewhat mysterious. We know it exists, but it's mysterious. The group action here is very explicit. So this, you can think of this norm, think of this telescope as a substitute for the Lubin-Tate spectrum, the fourth Lubin-Tate spectrum. Yeah, you can think of this telescope as a substitute for the fourth Lubin-Tate spectrum. It has a C8 action on it, because, and that C8 action is really easy to understand and calculate with. It's much easier to calculate in this world than it is in the Lubin-Tate world.
You somehow saw the patterns already in one of these higher real K theories.
Sorry?
You saw these patterns already in the higher real K theories. I mean, something like a gap theorem.
No, the gap theorem we didn't see the gap theorem. The gap theorem only comes in when you adopt the slice point of view. And I think it is possible now to define a slice spectral sequence for the Lubin-Tate spectrum. But that required, maybe Jeremy Hans or somebody like that has figured out how to do this, I don't remember. One of these young guys in Boston has figured out how to do how to use slice techniques on the Lubin-Tate spectrum, but we didn't know that at the time. That was certainly not available 10 years ago. So we have the slice machinery for this kind of thing, for these norms of MU, but we didn't have it for Lubin-Tate.
Did you have periodicity?
What?
Did you have periodicity?
Well, that came out of, once you get familiar with these slice calculations, you can get periodicity.
But without the slice? I mean,
You mean this thing without slices?
no, I mean Lubin-Tate.
Oh yeah, you do have periodicity in Lubin-Tate. Sure, you do.
No, but did you know that the periodicity was 2 to the 8th?
I don't know. We probably could have figured it out if we had to, but I don't think we considered that because we didn't have a gap theorem. I mean, you know that if you take.
But you said you were playing with this higher real K theory, so.
Okay, so
Periodicity would
if
be
you
one
take
of
the,
them.
you know as well as anybody that if you start with the Lubin-Tate spectrum, take the homotopy fixed points of a finite group, there's going to be some kind of periodicity, and you can and there's ways of calculating what it is, I don't remember if we actually tried that, but periodicity isn't going to do you much good unless you have a gap theorem, and there was certainly nothing like a gap theorem for anything related to a Lubin-Tate spectrum at the time. There may be now, but after the fact, but not then.
After the fact, if you go back.
I mean, but what I mean by after the fact is if you know you can do slice, if you know there's a slice spectral sequence for calculating homotopy fixed point sets of Lubin-Tate spectra, if you know that, once you're in the slice world, then the gap theorem, you can do the gap theorem because of something really simple that happens with slices.
But if you look at the previously known calculations of homotopy fixed points, you did have gaps. I mean, maybe nobody paid much attention to them, but there were always
not.
gaps below. So I mean, there were a few trivial groups.
Okay, I don't know the.
So it didn't occur to me that this would be sort of something which.
Okay, I don't know, I'm not sure. I don't know the answer to